So yeah, so today we're going to talk about support vector machines, right? So section 36, Eli went over, was it ensemble methods last time? Is that right?
Yes. Mhm.
Cool, awesome. So I know I've seen some of you guys before. So a couple of you guys might be, new, at least to me, right? So I just wanted to share this repo I have. I think I put it in the Zoom chat already. But this is where like my notebooks. So if you want to take these notebooks, for example, and like, you can fork it yourself. You can kind of like take those parts and play around with it. Today we're going to talk about in machine learning, support vector machines, and we're going to basically be mostly in those two notebooks today, right? We're talking about the support vector machines and the kernel trick. So the first thing kind of going through, we already seen, in this case, you guys should have already seen decision trees, random forests, right? And then ensemble methods, random forests, probably ADA boost, right? XG boost. So those are different ways for you to combine multiple classifiers together. Support vector machines are not going to be a ensemble method. Like you saw before, they're going to be kind of like another separate machine learning algorithm, just like you've seen like with decision trees. Okay, but they're a really powerful machine learning tool, and it turns out it was really useful, like in the 90s in particular. Support vector machines like really kicked off a lot in like machine learning. They're very useful. Nowadays, they're a little less played off or talked about as much, just because they're basically older cousin, neural networks can do a lot more complexity in there. And sometimes support vector machines can run a little slower depending on the hyperparameters you give it. But it's useful for us to talk about and like actually go through. So I actually found this like little thing online. I support vector machines, which I just thought was kind of cute. And no, they're not sponsored or anything like that. I don't get any kickbacks, but you can buy their shirts. I did look into it, say, oh, it'd be kind of cool to have this part. But we'll actually see this today a little bit of like where support vector machines come from. Note that this is another supervised learning technique. I think it's the last supervised learning technique before you guys go into unsupervised learning, which is like clustering and PCA, which is going to be sections 37 and 38, right? Because it's section 36. Yeah. So note there's another one we could. What's really nice about support vector machines is that we basically can decide a little bit if we care more about the boundaries or we care more about the actual accuracy of the data points being done. So note that's very different from decision trees. Decision trees, we specifically say, hey, we need to make the accuracy as good as possible, which we saw with a pure vanilla decision tree. It tends to overfit, right? Which is why random forest is so nice, because random forest allows us to basically adjust a little bit and try to get a little bit of extra, fuzz in there so it doesn't overfit. It's not too confident. Support vector machines, we can kind of do something similar by adjusting certain parameters to say, hey, I care more about the boundary than I do with the specific data points. So that's kind of like the idea of like what this better boundary, like why we would want this. Okay, so I kind of want to have this like overall question in your head, like why would it be better to have a defined boundary over accuracy? Okay, so some motivation, right? It's kind of like saying, all right, we have these two plots. So I'm going to go ahead and plot these data sets right here. And I have these two different lines already set up for you guys. Don't worry too much about the code, just kind of like me kind of playing around so you can see this graph, right? So we have the purple group and the yellow group over on the right side here. And we have two lines. We have this blue line that's going from basically from this corner to this corner, and this orange line kind of splitting between the two. I want someone to tell me, which would you say is the better line? They both separate them, right? So if you imagine like on the blue line, all the purple are above it, all the yellow are below it. On the orange, everything to the left of it is purple, everything to the right is yellow. So they perfectly split up the data set. But which would you say is the better boundary in this case?
I would say the red line is better because there's a purple dot really close to the blue line.
Okay, good. So you say like this purple dot just seems like a little suspicious that it was just way too close to this blue line. All right, George? Yeah. Cool. So yeah, I think there's a few other ways. I think for the most part, like people intuitively understand like, yeah, this orange line seems like the better model, right? Or seems like the better separator, okay? And so this is where basically support vector machines try to formalize that, say, how can we represent that mathematically, other than the fact of just saying like, oh, it looks better, right? And so the main idea here is that it's not so much that either of these the divisions are making a worse judgment. It's that we also care about where the boundary is defined. And hopefully that makes sense, is that kind of like, I think what George is saying, like with this purple point right here, it being so close to the blue point, it's almost like we're implicitly saying, hey, like, we are confident that there will never be a purple point below this thing. And like just looking at data, it's like, just because there we don't see any examples, we can see maybe it's a little bit off to the side here. So the more kind of buffer we have, the more confident we'll probably be when we get new data that looks similar to our original training sets. Okay. So again, the main thing is that accuracy isn't everything, right? We really care about these boundaries, and that's where support vector machines are going to basically be super nice, is that they're going to help us define the boundaries as best we can. Okay. So kind of like going off is like, how do we define a better boundary, right? So this is where it's like, okay, how do we mathematically show this? One way we can basically say it is saying, hey, we want more space. So kind of like what George said with here, the point being so close to this line, is we want to build up as much space as we can on between this like separation. So this is where we define this thing called the margin. Okay, and the idea of the margin is kind of like, a page margin, right? It's basically saying how much space, how much buffer do we have between the data points in the actual separator. So this is where I can show you a little bit of what that margin looks like. So you can see here, I changed the color to blue from orange, but you can see that it was originally that orange line that separates through here. And I have these little dashed lines that go from yellow to red. And you can kind of imagine that being like parallel lines that are kind of expanding outward. That's our margin kind of going outward. So the more like kind of outward we can go, the better, right? We want it to be able to expand further and further away from each other. Okay. So this is where it's like, okay, I think we got an idea, like we want this thing called the margin to be as big as possible. Like, what do we do from here? So what we can say is, all right, there's two kind of things we can kind of check out. There is how many are misclassified, essentially how many purple points are on the wrong side of the classification. So if we imagine we had a purple point over here, then this boundary is probably not doing a great job for classifying, right? So that's one type of error. And the second error is basically how bad of a boundary do we have, which is basically saying, do we have a good margin or not? So you can imagine back to the very beginning up to here, is that this one, they both have good classification error, right? Basically classification error of 0, but their boundary error, their margin error, this blue one right here going diagonally is just gonna be a higher point because basically there's not much of a margin we can fit between these two, okay? So that's the idea where we have these two kind of different errors being put together into one error term. And remember, the way we decide on machine learning algorithms, how we learn, right, on machine learning algorithms, is we want to minimize the error. We want to minimize that loss function. And then, that loss function for each individual, and overall the cost function, right? The whole point of gradient descent is trying to minimize the error and get it as small as possible, okay? So this is where one thing about classification error, I debated about talking about this like in the margin error and saying like exactly how is this calculated. This is where I kind of debated, it's like, oh, like how much should we really go into it? But one way you can kind of think about this is that if you start off essentially from this side here and count outward, is that as this first margin right here, as you count outward towards this direction, is saying if you have a yellow point over here, you're more okay with that than if the yellow point is over on this side right here, because you're like, okay, like, well, it might have a couple over here, but as we expand outward and outward, we're like, okay, there should be more on this side. So you can actually have a decent margin, even though they're misclassified points. So note that basically we start basically labeling this as kind of, what's it called? Like these lines, like if you imagine, try not to get too mathematical here, but if you imagine like this line right here is y equals x1 times some number, right? So some number plus x2, the axis right here, times w2. And then this y can start off with, like, let's say just 0. And then the next line would be like, oh, that would be like 1 equals that same equation right here, or that expression. And then this would be 2 equals that expression right there. And you can use these values of 1 and 2 basically saying how much of an error you're kind of contributing in there. Is that if you're on this line right here on this parallel, you're contributing an error of 2, or so on. And then we can do the opposite way. We can do -1, -2 here. So just know that that's how it mathematically we can kind of determine this classification, or not the classification, this margin error, essentially we can build it up with these parallel lines and say, where do these individual points land on the parallel lines? So we'll minimize it in that way. And note that I have negatives here. So if you swap them, you just multiply by a negative number, and essentially it'll become positive. Okay. So I'm not expecting you guys to really like say, oh yes, I understand that now. I'm just kind of showing you guys a little bit like where that math comes from. But any questions overall about like the margin, like how that is represented? Okay. I think conceptually people will understand this part pretty well, right? Someone have a question? No?
Yeah, it's me. Oh, Can you hear me okay?
Yeah, you're good.
Okay. All right. The red, the orange, what do the lines really mean again? I know the blue was the separator, and then those are the margins away from the separator? Is that what they represent? Yeah. Okay.
That's right. They're representing it like as we get further and further away, they're basically saying how big of a margin can we put between like this separator in the group of points.
Okay. And then you determine the distance between the margins and the separator by?
Right. So I guess what I was trying to get at is that, let's say, for example, I'm going to write in purple because purple is probably easier to see, is let's say we have a purple point, like let's say it's pretty close, like right over here.
Gotcha.
Is that we want to say, well, how far away is it from this line? But how do we say it's far away, right? It's like, well, we could measure the distance from here to here, but we could also measure the distance from here to here or from here to here. So it's not like, it's like, oh, what does it mean by far away? And so what we do instead is we build up these parallel lines here. And wherever it falls on those parallel lines, that's the distance from this linear separator.
Okay. Okay.
Does that make sense? That's probably clear.
Yes.
I'll be honest, like the way I explained it, I feel like
you.
it might have been, it might not have been the most clear. So hopefully that kind of clears things up.
Okay. Yes, that helped. Thank you.
Okay. No problem. Okay. So let's go into then and say, okay, let's go to say how we make this error margin. So note that this is basically going through the same thing, right? Is that we have that Wx plus b. So note that I put W here being like a matrix or like a vector, right? So no, you have like W1 times X1 plus W2 plus X2. I'll tend to use W just because you'll see it again in like neural networks and other machine learning algorithms. But essentially this is just a set of numbers. So this is very similar to like our linear models and stuff like this. So classification error, it's pretty simple. Basically, it's just saying how many times, yeah, okay. We start from our margin. So I should just say separator. This should not be margin. We start with a separator here and we count outward to see what the error is instead of the center, right? So the idea here is that it's like, okay, like how many things get wrong? And then margin error basically saying how big of a value can we get over here? And it turns out we can just simply look at saying this W here, which is basically saying how big of this margin until we get this error in here. And what's kind of interesting is that this turns out to be the same thing as L2 regularization. So really what's saying is the absolute, not absolute value, but the squared value of this part. So our margins are just going to be defined by saying how big of this error we have, which is basically saying, all right, we have W1, W2, W3, how big are those weights? Essentially, how big are these guys in here? And that will actually define our margin mathematically. It turns out those are equivalent. Like, I'll be honest, like going from here to here seems very like, wait, like how does that even work? This is where like if more linear algebra might be, help you kind of go along with saying, oh, this is how it's defining. But basically it's saying that if we have large weights, essentially, is that this is kind of equivalent to having a bigger margin. And so we want to actually minimize this as best we can. And so that's why we actually have it's kind of equivalent to L2 regularization, which is why support vector machines work really well with overfitting, because essentially we're already regularizing it. Okay. But the main thing I want you to kind of know is just that our margin is defined directly from these weights that are built from the separator itself. Okay. So they're not defined directly from the classification. Okay. And then once we have this error term, right, which is basically the error of the classification, error of the margin, we just use gradient descent to minimize that part. Okay. So yeah, in general though, when you actually implement these algorithms, you won't have to pull out like what is the classification error explicitly, what is the margin error explicitly. Mostly what we're going to be using it is this hyperparameter called C. And this C hyperparameter right here is going to determine saying how much should we care more about the margin or care more about the classification error. So what this modified error total right here, which is the thing to actually use gradient descent to minimize, will basically be C times the error of classification plus the error of margin. So note that that C basically is just some value, some number we're giving it. So kind of a question is like, what happens if we make C very large? Okay, what does that mean? What errors do we care more about if we make C very large? Based on this equation here.
We care more about classification errors.
That's right, right. So by making a larger C value, we care more about saying, are we going to define it really well? So if I look back all the way to this guy right here, and let's just say, let's make one that's just going to make both of them wrong. Let's say I do, or let's say I have this one. Let's like this. Oops. I make a purple point right here. So now the blue is still doing perfectly well, and this orange is going here. By turning up C, we're saying, hey, blue is actually a better model because maybe for some reason, for whatever model we're looking at, whatever data set we're looking at, we care more about the classification over the actual boundary. So these are hyperparameters that you need to tune to decide. And there's not a right answer in a lot of ways. It just depends on what, in a sense, you care about. In the same way, you might talk about an F1 score or an F beta score, is that it just depends. Do you care more about precision or recall, or are they equal to you? Okay. So yeah, and this helps. I think hopefully this gives you an idea then when we actually use that parameter C when we implement this in sklearn, is saying what are we doing when we change that C hyperparameter? We're basically saying we care more about the classification. Okay.